We're still talking about dynamic programming, and I finished RNA folding last time, although we never did really the traceback completely. But that makes a good exercise for you to think about how you do the traceback, and make a good exercise for your homework or an exam type question. Today I'm going to talk about the third dynamic programming problem that we're going to see. We may see some dynamic programming later, but this will be enough in terms of the formal explicit discussion of dynamic programming. And this is shortest path, not like Dijkstra. Dijkstra was shortest path in a graph, but it was under the assumption that all the edge weights were non-negative. And sometimes it's useful to have negative edge weights. They have some meaning in the problem that you're trying to solve. So we're going to allow, so this is the shortest path in a directed graph. So all the edges have directions, a directed graph, and it's weighted. Edges are weighted, or you can just think of edges have costs. Okay, so here's an example of a and negative edge weights are possible. Okay, so this might be a 5, -3, -7, 8, 6, whatever. So it's advantageous if you're trying to find the shortest, the minimum total weight path. It's advantageous to take some edges that have negative weight. Minimum total weight path, or cost, from some initial vertex or node we'll call S to some final node T, from S to T. T for terminal, S for source. Okay, now we're allowed both positive and negative weight edges, zero weight edges too. But there is one restriction, which is that there's no negative weight cycle. Okay? So assume no negative weight directed cycle. So a directed cycle is one where you can go around it never going against the direction of an edge. So here's a directed cycle. Okay. Here's a cycle. If we weren't considering edges, this would be a cycle, but this isn't a directed cycle because any way you would follow it, you'd have to go against one of the edges, so that's not a directed cycle. So we're assuming that even though there are directed cycles, well, there may be directed cycles, but there are no directed cycles that have total negative weight. So if this is a 10 and this is a 3, then if this is negative, it's got to be larger than negative 14. So it might be, oh, sorry about that. Sorry, I'm in class. Okay, well, told her not to call me here. Anyway, sorry, that's supposed to be a joke. Okay, so this is larger than negative 14. Okay, so negative 10, for example, which is, by the way, negative 10 is larger than negative 14? Okay. So negative 10 would be okay because this total weight now is 3, and that's not negative. The reason you don't want negative weight cycles, well, there's really two reasons. One is it's not clear what it would mean to find the shortest path if there was a negative weight cycle. But if a negative weight cycle in a graph, let's say this is a cycle here and has negative 10, and here's S, and you get to that cycle, and here's T. What's the shortest path distance from S to T if there's a negative weight cycle? negative infinity. You can just keep going around this thing forever, although you might say you'd never gotten to t. So in graphs that have a negative weight cycle, it's not clear what the meaning of the shortest path is. Now, you could say, I want the shortest path that doesn't contain a cycle. That would be a meaningful statement, even if there are negative weight cycles, but that's a different problem. And it's more difficult to solve than the shortest path problem when there just is no negative weight cycle at all. Okay, so later we might consider that problem, finding the shortest path when there are negative weight cycles, but you're not allowed to use a cycle. But that's a much more difficult algorithm and more inefficient algorithm than under the assumption that there are no negative weight cycles, directed cycles at all. Okay, now what's the first idea you might have in approaching this problem? Or maybe it's already been excluded because you've thought about it. I think in one of the homework questions there was a question that asked whether Dijkstra's algorithm will work correctly if there's a negative weight cycle, and the answer is no, it doesn't. So your first idea might have been, well, let's just try Dijkstra's algorithm because we know Dijkstra's algorithm and it works correctly for the case of no negative weight cycles or no negative weight edges, actually. Oh, that's another good question. I don't think Dijkstra's algorithm was assumed correct or proven correct with the assumption that there's no negative weight edges, period. So you might want to look into what happens if, no negative weight cycles. No, that's what we're considering now. So yeah, Dijkstra's algorithm should not work correctly if there are negative weight edges, period. Okay. So Dijkstra's algorithm won't work right. We need something else. So the general framework of what we're doing right now is dynamic programming. So we want to think of a kind of a recursive approach to this problem. It turns out there are a lot of different recursive approaches that you can make work, and each one has different advantages and different ways you can embellish it and extend it and so on. Actually, the one that I like most is not the one that they talk about in the book, but I'll follow what the book does. So thinking recursively, we have to think of ways of describing subproblems and come up with notation for the subproblems, and then come up with a recurrence for the subproblems, and then see how to evaluate all of the values. It's sort of all tied together. So what are some kinds of subproblems you might think of? I mean, how do you restrict the full problem to something that's some easier version of it, a subproblem with less data in it? Any suggestions? Or less constraints in it, less something in it, because that's what recursion is all about. It's getting more for less. Yeah. Or more from less. Anybody have an idea? Doesn't have to be a right idea. Any idea. Okay, well, I'll give you one. We're going to define opt IV to be the minimum cost of a path. And the paths have got to be directed. You can't go opposite to a directed edge. That's going the wrong way in a one-way street. It costs infinity if you get caught doing that. So opt IV is the minimum cost of a path from some node V to T. Okay, so this is already some kind of restriction because some kind of different problem, because we're interested in the problem from S to T, and now we're making it, I don't know, should I call this a restriction or actually making it more, generalizing it, because now we're allowing any node. But, all right. In order to solve the S to T problem, we're going to actually solve the problem of shortest paths from each node to T. So from V to T, using at most I edges. Okay, so this is really where the subproblem comes in, because the full problem is that you want to find paths in the graph and without any restriction on how many edges they use. So here, by restricting I, that's a subproblem. But this bothers me. I wanted to make this sound like a subproblem, and yet this V is not S. It's not where we're supposed to start from. So that doesn't feel like a subproblem, does it? It feels like just a different problem. Okay, so somebody really should object that this isn't fitting into the framework of dynamic programming because of that. Does everybody understand what I'm uncomfortable about? If I'm trying to make this look, so how I'm going to change that to make this really look like a subproblem is say that our problem now is not to find the minimum total weight path from S to T, but to find the minimum weight path from V to T for each V. So what we really want to return is for every node in the graph, what is the shortest path to T? So T is specially designated, but the problem now is for every node in the graph, what's the shortest path from it to T? Okay? And then if this is my general problem, and if I have here I specify an I and I specify a particular V, then I'm saying what's the minimum cost? The minimum cost of a path from node V to T using at most I edges. That is a restriction. That's a subproblem of this, right? Okay, so this fits better into the whole framework of what I'm talking about, a recursive, well, at least making this a subproblem, and then being able to say that our recursions and our dynamic programming always wants to look at subproblems. Okay, so this is what we're going to focus on, and given that, what is it that we want? With this notation, what's the notation? What's the problem we're trying to solve in terms of that notation? At least in terms of the weight of the path, not necessarily the path itself. How do we use this notation to express this problem, at least finding the shortest path distances, not necessarily the path itself? Now that I've done the midterms, I know everybody's name. I'm going to start picking on people randomly if nobody volunteers. Okay, yeah.
Up to NS, using all the nodes from S.
Okay, that's close. Opt, well, this is using at most I edges, and how many edges do we have? Well, there's as many edges as there are in the graph. We can give it a symbol M. Okay, but a little bit of thought, you'll realize that since there's no negative weight cycle, the shortest path is never going to use more than n minus 1. If n is the number of nodes, the shortest path will not use more than n minus 1 edges. Because if it uses more than n minus 1 edges, it has to have a cycle. That cycle can't be negative, so it's either positive, and it's definitely you don't want to use the cycle, or it's 0, in which case you can get rid of it. So we'll just say n minus 1, because that's the most number of edges that you could ever really realistically use in a shortest path. So you have the opt, n minus 1 edges, and what do we want to put here?
S.
Well, S if we were going to the original problem that I stated, but in terms of the new problem, it's V, and then we want to say for all V. because the new problem says find the shortest path from v to t for each v. So this is what we ultimately want to know, is opt n minus 1 v. Okay? So we've got the recursive notation where we have our goal, what we're trying to ultimately compute. Next thing we need is the recurrence relation. So opt of iv, well, as in most recurrence relations of dynamic programming sorts, you have some choices. Okay? So the choices, what's the obvious first choice? This is allowing you I edges. You want to go from v to t. Well, maybe you don't need all I edges. Maybe the best thing to do is to use at most I minus 1 edges. And maybe there's a path that doesn't use very many edges. So you better put that in as a possibility, opt I minus 1 v. Okay? But if you do want to use I edges, and that means exactly I edges, from v to t, then your first edge is going from v to some other node. Let's just give it a name w. And from w, you're taking a path from to t, and how many edges does that have in it? Yeah, exactly I minus 1. So this is the case when we're looking at paths that have exactly I edges, because I minus 1 or less is already in here. So this is I minus 1 edges. So we have to include opt vw, opt w I minus 1. That's what's going from w to t, plus the weight of this edge from v to w. Now, I don't think I give you notation. In the book, this is cvw, the cost of the edge vw. Okay?
Are your arguments we switch in the second opt?
Say what?
Are the arguments what we switch in I minus 1 comma w, or w comma?
Oh yeah, right. The arguments, yeah, right. They're supposed to be in different order. I minus 1 w. Okay. So I minus 1 w, but which w? So I just drew a picture here. It's a cartoon. You go from v to w and then from w to t. But in terms of the algorithm, which w are we talking about? Yeah.
Every w?
Yeah, all possible w's. I mean, that certainly would work. So this is w contained in capital V. Capital V is the set of all vertices. So you're going from v to w, which might be infinite because there may not be an edge. Okay, so if there's no edge from v to w, that's infinity, and this will definitely not be a good choice. But formally, it's fine to include that. And then from w to I minus 1. And so if this is overall w, then you want this to be the min of that, right? You want the smallest that's possible, where you go from v to w and then w to t using I minus 1 edges. Okay, now there's a little subtlety here. The way I divide it up, oh, and by the way, yeah, before I go on, this is the min overall w, and then we have these two possibilities. What's the best thing to do between these two possibilities? Take the min of those. Okay? Now there's a little subtlety. The way I explained the way we divided up the cases, this is the case when the path from v to t uses I minus 1 edges or fewer. Okay? And then we had the case when we're using exactly I edges, so one edge here and then exactly I minus 1 edges here. But the notation, I minus 1 to w, or opt I minus 1 w, that's not talking about the optimal path from w to t, or the shortest path from w to t, when you use exactly I minus 1 edges. Okay, this notation is the weight of the shorter, the cost of the shortest path from W to T when you use I minus 1 or fewer edges. Okay, so this doesn't exactly mirror the way I logically divided up the two cases. Am I in trouble? Is it okay to leave it this way, even though it doesn't perfectly match the way I was dividing up the two cases? I see some people nodding yes. No no's. Somebody want to explain the yeses? Okay, well, the issue is, well, first of all, let's just make sure this is sufficient. That is, if the shortest path from V to T really does have exactly I edges, have we included it here? Well, not in this term, because this is the paths of I minus 1 edges are fewer. But paths of exactly I minus 1, exactly I edges would be included here. If it's true that the shortest path from V to T does actually have I minus I edges, then it will look like this, and this will be a shortest path from W to T for some W that has I minus 1 or fewer edges. So we are okay in the sense that we've included the possibility of a path with exactly I edges. But suppose that the shortest path from V to T, okay, is I minus 3 edges, okay? So the shortest path from V to T has I minus 3 edges. Will it show up here? Yeah, because it's a path that uses I minus 1 or fewer edges, and it's the best. If it's the best from V to T over all paths that have I or fewer edges, it's certainly going to show up here if it actually has I minus 1 or fewer. Is it going to show up here? Okay, so this includes the possibility of using I minus 1 or fewer edges to get from W to T in the shortest possible way. And if the shortest path from V to T over all paths that have I or fewer edges has actually I minus 3, then this portion of it from W to T is going to be the shortest path from W to T that has I minus 1 or fewer. In fact, it has I minus 2. Okay? So what's going to happen in those cases is this will be a value, which will be the minimum of these two, and what will be the value from here? In the case that the path actually has I minus 1 or fewer edges, the shortest path from V to T has I minus 1 or fewer edges, that shortest path value will show up here by definition. Will it also show up here? Okay, well, I've lost everybody. Yes, it will. Okay, and that's the subtle point I was just trying to point out, that even though I described these two cases as a complete dichotomy, this is when it's I minus fewer edges, when the shortest path from V to T is I minus 1 fewer edges, and this is supposed to take care of the shortest path from V to T when it's I edges. In fact, if the shortest path from V to T has I minus 1 or fewer edges, then it'll show up in both cases. So actually, when you say it like that, or when I just said it like that, you may kind of wonder, why do you need this one then? Oh, no. Sorry, this is for I minus 1, and this is for even less. This will show up the ones that are even less than V to V. Anyway, something feels redundant here. This is okay. Okay, this works, but feels like there's some redundancy, and at the moment I'm wondering whether we can get rid of that. But I was just trying to point out that in the case that the shortest path from V to T really does have I minus 1 or fewer edges, that both of these will light up as the shortest. Okay, but this will take the one where it's exactly I, and so we need that definitely. Okay, so think about that for next time and tell me whether there's really a redundancy or not. Okay, so I think I've confused you enough about the recurrences. these are recurrences, and they definitely work. Whether they're a little overkill is another question. So let me call these recurrences star. And then we want to organize the computation of this as a dynamic program. And as before, you could always organize this as a top-down algorithm, top-down recursive algorithm, where your first call would be opt n-1v, and you'd make that call for each possible v, and you'd spawn a huge recursive tree, and it would be very, very inefficient to do that. Instead, we want to do it bottom-up. Bottom-up means you're going to compute first the smallest subproblems, the subproblems where the parameter here is the smallest possible, and then work your way up by using this recurrence, always making sure in the way that you've organized the computation that when you're trying to compute opt-iv, that you've already computed the particular opt values that are called for in the recurrence. Okay? So when you look at this, opt-iv, well, it needs I-1, v, it means I-1w. So it looks pretty clean, pretty simple, a lot easier than the RNA kind of computation that we did last time, because this is certainly suggesting that you'll just let you let the first parameter here increment from say 0 up through n-1. And for every value in here, you want to look over all possible starting vertices. Okay, so that suggests 2 for loops, right? So M is going to be our table. I don't know why, when opt was the value, I mean, opt is clearly a function of 2 parameters, why it can't be the name of the table we build. But in the book, they usually switch to M for the table. Equals 0. So this is saying, what's the shortest path from T to itself using 0 edges? 0. Okay. And M0v is equal to infinity for v not equal to t. So these are the base cases. The shortest path going from v to t using 0 edges is infinite, and unless you're already at t. And then for I equals 1 to n-1, so this is the number of intermediate, this is the number of edges that are being permitted in the path, and we're going to vary from 1 to n-1, and that's what I was saying over here. It seems sensible to just let the first parameter increase that way. That would work. And then for each vertex in the set of vertices, compute MIV using the recurrence star. Well, you can't compute MIV using the recurrence star because the recurrence star is in terms of opt. Okay? But if everybody understands that the book did the sleight of hand where they were calling things opt and now they're calling things M, you can use these recurrences just wherever you see opt, make it an M. So you can compute MIV using these recurrences star. And you want to check that that actually works. That, as I was saying, when you want MIV, this tells you need MI-1V. Well, the outer loop is changing the I, and this is smaller, so that should work. And you need I-1W. And what you have is, again, the outer loop is changing I, and the inner loop goes through all possible V's. So when you need to look up those values, at the time you're trying to compute this, you have them, and everything works fine. So that, and then return M of n-1 V. For each V. Okay? All right. So we argued that the recurrences were correct. this is very clearly a correct implementation of the recurrences that you can that works because it always has what it needs at the time it's trying to compute MIV. What's the running time of this? So the primitive operations, we have to do lookups, we have to do addition, and we have to do comparisons. So for a particular IV, how many operations, for a fixed I and V, how many operations are required here? Yes, and right, because you're looking over all vertices in the vertex set, so it's certainly bounded by n. Okay, so order n for each evaluation. Compute this. That's order n time, and then we have two loops that enclose that. Each one, this goes around n times, and this is again bounded by n. So we have n squared around this. So n squared, and that means the total time is bounded by order n cubed. So in n cubed time, we're able to compute n minus 1, m of n minus 1 v for each v, and that means we know the shortest path distance from each vertex v to the specified t. We know that shortest path distance in this order n cubed time. Now Dijkstra's algorithm, I think the first analysis of Dijkstra's algorithm was n squared, right? And in Dijkstra's algorithm, well, Dijkstra's algorithm has one origin, and we're actually computing its distance to everybody else. So this looks like it's more expensive. Actually, it turns out that we can actually compute the shortest path between every pair of nodes in n cubed time. But this algorithm doesn't do that. This computes the shortest distance from every pair of every node to t. So there's one specific destination t. So we get n cubed there. All right. Now we can actually reduce the running time somewhat. One of the improvements we can make over here, instead of saying we're going to optimize over every w in the vertex set, the only w's that are relevant really are the ones that are neighbors of v. Okay, so we could specialize that a little bit. W, well, opt over w where v to w is an edge. Okay, and if you have the right data structure for the graph, you can get these in constant time per w. You wouldn't want to use an adjacency matrix, adjacency array, because that wouldn't really help you. You'd still be looking through all the possibilities. But if you use an adjacency list for each node, then when you're at v and you want to pick up the w's that are relevant, you just run down that adjacency list, and therefore the time to evaluate this is no longer order n. What is it? So if we have a particular I and a particular v, what's the time to evaluate opt IV? Before we just said it's order n, big O of n, which is true. It is bounded by n. But now we're saying something a little more precise. It's bounded now by the degree of v, the number of neighbors that v has. So with this one, it's order the number of neighbors of v, also denoted the degree of v. So if this is v, the degree of v is 3, even though there might be thousands of other nodes. And in most graphs, the number of nodes that go out of number of edges that go out of a node is much smaller than the total possible. So with that, then the time bound is, I'm running out of time here, but ultimately it's, well, I'll just tell you, it's order nm. M is the number of edges. Okay, and you should read the book to see how that was achieved. order nm. Okay. The other thing, I'm running out of time because I want to spend enough time giving out the midterms, but the other thing that I was going to talk about is how to reduce space. So space here is order n squared because we're keeping a big table, M, that has two parameters, each of which ranges from 0 to n, or 1 to, anyway, each has n possible values. So this is a table of size n squared. But because each iteration, I mean by iteration, for each value of I, here, iteration of the outer loop, we're only looking at I minus 1. So if you think about filling in this table M row by row, when you're filling in row I, you're only looking at row I minus 1. Okay? You don't need the values prior to that. And so that tells you already that you could limit your space to 2 rows. The previous row and the row you're filling in, and then your algorithm's got to kind of flip-flop back and forth. Which one is the previous one, which is the current one. And then if you think about it even further, you can convince yourself that you really only need 1 row, and I think maybe 1 more cell beyond that. But you can limit your space down to order n from order n squared, and oftentimes saving space is a very important thing. Okay, I think that's all for this dynamic program. Oh, except for the traceback. We didn't do traceback, and I wasn't going to anyway. That makes it, and the book doesn't, for this problem. That makes it a good homework question to think about how you would organize the traceback in this problem. Actually, what the book does do, they don't talk about the traceback for the n cubed version or the n squared space version, but then they say when you've used only order n space for your table, it makes the traceback trickier. And they do talk about how you would do the traceback if you only had order n space, if you're only keeping that smaller array and not the full matrix. But how to do the traceback when you're keeping the full array makes a good homework question, so you might think about that. Okay.